Hey everyone, we are going to check out and see how you did on this example that I asked you all to do on your own. So this is an example of the COSECANT function. It's our first time graphing one of the reciprocal functions entirely on our own. We went over the parent function. We went over one example together. We also have graphed sine and cosine. We did those parent functions. We did an example together for each of them with full-blown transformations, and we did one on our own of each type, and we checked those. So now we're on COSECANT. This is the first example where I'm asking you guys to take an extra step when it comes to this area of your function right over there. Normally, I give you the equations set up fairly nicely where you are able to see clearly your A value, which we already see, it's 2/3, so a vertical compression by a factor of 2/3. We see which trig function we're working with, in this case, COSECANT. Don't call it cosine. It's not. This is COSECANT. Practice saying the name. And then sometimes you don't have this parenthesis here necessarily, but you would have your B value next, and then you may have a parenthesis showing your X or your theta minus or plus, if it's minus a negative, your H value, where your H is your horizontal shift. So you either went to the left or to the right. Sometimes we call that a phase shift, okay? Phase PHASE. And then plus K at the very, very end. So if you look closely, you could see that the difference here is somebody had come along and distributed this B value into the parentheses where the X minus H stays. In the event that that happens, I'm just focusing only on this part for a little while, you get BX, which that part's fine because you could still easily identify your horizontal stretch or compression factor, and you could still figure out what the period is accurately because you're just pulling the number from in front of your input or your X or theta, whatever it might be. But this next part, minus BH. Now, obviously I'm using stand-in letters. These aren't numbers right now. So it's pretty clear that this represents the product of B and H. But if you were using actual numbers, you would get a new number. You would get a new fraction. You would get a new integer, whatever it might be. So when you have a new number, it's not always as easy to recognize like, oh, I should be pulling out the B value in front so that I can identify my phase shift. In the event that you are given an equation in this form, which would look something like this, and if you flip back and compare it to your other examples, I hope you haven't been lazy and dropping parentheses. You are completely changing the equation, all right? You have a couple options. I'm going to focus on two options right now. Option number one is the one that I will usually do, and that is where I'm just going to take whatever that B value is, and I'm just going to factor that out. How do you factor that out? It's not always easy. I know if it's something like a 4 in an example like this one, not so bad because this one's set up nicely for you. But what if you have to factor a 2/3 out of a 7/13? Then it's not so easy, right? So let's talk about how distribution works and therefore how factoring works, because they are the same operation in opposite directions, right? So when you distribute something, you multiply it inside of the parenthesis. When it was on the outside, where did it go? Well, we often think like we plopped it in there and we plopped it in there. Sure, you could also say I multiplied everything inside by B and I divided what was outside by B. B divided by B is 1, so it goes away. Bye-bye, multiplicative identity, love you. And the inside, we multiply by B, we get our new values or whatever it may be. So I'm going to do that in reverse. I'm going to multiply, I should write it over here, multiply outside of the parentheses by B, and then I'm going to take what's inside, BX minus BH, I'm going to divide everything inside by B. This keeps it balanced, multiplying and dividing by the same number. It's just like multiplying or dividing by 1. It's what you do when you rationalize a denominator. It's what we do to find common denominators. It doesn't change the value of something. It just makes it look different. Then from there, b resides out front, and out inside, you use our pretzel method to reduce whenever you have a plus or a minus in your numerator or multiple plus and minus signs. And b over b is 1, not 0. So you're left with x. b over b again is 1, so you're left with minus h. Now it looks pretty nice and easy here, clean, because we're just using the b's and the h's. I'm sorry. Go get it. Go get it. Go get your lamb, bud. So I would mostly worry about this. Another option that you'll probably see quite a lot, I do tend to notice that this is like another really heavy go-to method, but I don't necessarily think it's any better. In some ways, I guess it could be easier. However, I don't really like that it kind of takes away a little bit from seeing just with your eyes that phase shift, and recognizing the structure of an equation and how it's written and how it should look. So, it's, I don't know, questionable. If you like it, you can still do it. You just have to make sure you follow through with all of the rules. So what do we do in this case? Well, your b value is your b. B is b, like it's the thing in front of x. Great. But what about your shift? Your left-right shift, okay? What about, so we want to call it maybe the starting point. What about the starting point? So like the origin or 0 for your input, because it's not always at the origin, like sine starts at the origin and so does tangent, but other functions don't start at 0, 0, right? They start like 0, 1. What about the starting point or x value? How do we find it? So it's not BH. How do I know what H specifically is? So we take this whole entire inside, and we set that BX minus BH, we set that equal to 0. Whatever the BH is, obviously if it's minus, you do plus, but if it's plus, you do minus. No big deal. Here, this cancels. Cancel means 0. BX equals BH, whatever that number is, or it might be a negative number, remember. And then we have to get x alone, so it's attached to the x by multiplication. Even if it's negative, you don't add to get rid of it. It's being multiplied. To get it off the x, you have to divide, I promise. Then we divide by b, divide by b. Then these reduce, and you get just 1, so x equals h. Now that's giving you already the opposite sign. That's giving you your starting point. So if it gave you x equals 2, then you start at positive 2. If it gives you x equals negative 3, your first tick mark is left 3 units, okay? So it's already giving you that opposite number. Usually we kind of think of it as the bunker house, and we have to kind of go the other way. However, both of these have their downsides, and I'll make sure I plan for an example that is a little annoying for us to do together on the secant one maybe. But when you have a lot of fractions, which we normally do with radian measures, it gets annoying. And when you divide by a fraction, you guys have to remember it's multiplying by the reciprocal, all right? So we'll get to that. Keep this all in mind. And we're gonna leave this over here on the side, okay? I hope you copied all of this down. These are your two options. So I like option 1 a little bit more. It's sort of more in line with what we've been doing. And here is option 2. Okay. So let's get this organized. So y equals 2/3 can stay. Cosecant is the trig function we are working with. And I'm going to factor out a 4. So that means I'm going to multiply on the outside by 4. And I'm going to take what's inside, which is 4x plus 4pi over 5. A lot of you guys keep saying the word radical when you mean pi. Okay, gotta break that habit. Plus 8. That's what participating will help you with. If you participate more and you keep saying things out loud, you'll say the right names. Now, if we multiply out here by 4, we need to divide inside here by 4. Now, we have fractions, yes, we only have 1. It could get a lot worse because 4 could have been like 3/7, right? And you would be trying to factor a 3/7 out of 4 pi over 5, right? Here, pretzel time. That one's not so bad. The 4's just reduced. It should. And if it doesn't, you're not doing it right, correctly. So the 4's are gone. And here, so I'm just going to rewrite it one more time. Y equals 2 over 3 cosecant, parentheses, 4 reduces, right? X plus, so it stays plus. If that were a negative 4, you would have to use a negative and that sign would change. Dividing by 4 over here is the same as multiplying by 1 over 4. Dividing is the same as multiplying by a reciprocal. This should be a no-brainer if you are as far as pre-calc in your life right now, okay? 1/4, do not write 4 pi over 20. Do not write 4 pi over 20. No, you're better than that. Reduce, 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 okay? 4's are gone. Think smarter, not harder. Pi over 5. If you do things like that, you dilly-dally, you are not going to be efficient at all. You're not going to finish things. You're going to take entirely too long, okay? So we have our beautiful, beautiful equation, and let's get to putting this graph together. So a few things we want to look at. We have a cosecant. It is the reciprocal of sine. So when we graph cosecant, we draw inside, like within, a dotted sine wave. And then we kind of do a little flipperoo like we did in the other two examples. So the parent function and the guided example. So first thing I'm going to take care of is I'm going to go ahead and draw in my sinusoidal axis. So what I'll do is I'm just going to go right here. I'm going to try to not be as greedy with my space as I usually am and leave a little room here because I tend to write all over the problem, and then when I draw the y-axis in, I'm like, I regret this because now it's a mess. So I guess I could just label little y equals 8. That's taken care of. Next, we look at the a value. That's going to give us some more values on our y-axis, and our a value is 2/3. If it were a 1/2, I would probably honestly use a decimal and do like 8.5, 7.5. It's a fraction, and yes, fractions are our friends, but I'm not, and usually I would say, ew, you don't use mixed numbers, ew. You use improper, but here, in this case, let's be practical, we should use a mixed number because we want to know it's up 8 2/3 and the lower point, or, well, whatever, the other point below the 8 is at 7 1/3, you know? That just makes more sense in this case, okay? So we're going to get this drawn. Now, it's a positive cosecant. That means I'm going to sketch in a dashed positive sign. So I'm not going to go too high. I'm not going to get too crazy with the space I'm using. So I'm here, here. A graph like tangent and cotangent, you're going to see though, you really want to take advantage of your horizontal space, you know, like use as much as you can. But if you're doing this, you also got to be neat. Sharpen your pencil if you're using a pencil, and really, really be neat, okay? So here, this would be a little concave down, little hump, and this would be a little concave up, hump right over there. Next thing we have is, the other higher point, like I said, it's going to be 8 2/3, and the lower point will be 7 1/3, right? 2/3 below. So I have that. Since these are all positive, that means my x-axis is somewhere below here. Obviously, this is not to scale. When I draw my y-axis, I put the little zigzag and say, boop, we broke it, and put it back together. It's all great. Now, underneath each of these 5 marks, we put our tick mark. 1, 2, 3, 4, and 5. 5 tick marks, all taken care of. Everywhere that we have a 0, everywhere that I have a 0, for sine, cosecant is the reciprocal of 0, and the reciprocal of 0 is undefined. So I will draw a vertical asymptote at the first mark, the middle one, and the last one. Lovely. Ooh, hopefully it's not block too much of my big head in the way, so let me move myself and let me move that paper. I apologize. So sorry. Okay, how's that? That should be better? My bad. All right, I haven't looked up at that. There we go. So I'm working on making this cosecant shape. Not quite there yet. Now, this represents 1. I know it's not 1 right now, but just think about what it represents. What's the reciprocal of 1? 1. So this point on the sine wave is also on cosecant. They have that in common, and they have that in common. Those are the only points they have in common. If you think of like something in between here and here as being 1/2 of the way up, the reciprocal of 1/2 is 2. So the new point will be 2 units above. Something over here might be 1/3 of the way up, so the new point will be 3. Something that's like 1/100th, 1/100th of the way up is now 100 units up, you know, above the sinusoidal. So what does that do is it makes this little piece, this little curve right here, it's going to grow very rapidly upward. However, it's undefined here, so I will never touch this vertical asymptote, all right? But I will go up, 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 up forever. So as I approach this asymptote from the right, it's shooting upward. So as my x's get closer and closer and closer to this, what are my y values doing? They're growing indefinitely. They are approaching infinity. They'll never get there because you can't get there, but they're approaching it. This is good to know if you're going to do limits at the end of the year, which you are. So now same idea on this side, okay? As the x values get closer and closer to whatever this x value might be, my y values will be approaching infinity from the left. As I approach this same x value from the right, my y values, okay, think about it, think about the words that I'm saying. As your x value approaches, like your x might be whatever this tick mark is, and then we pick this x value, like above here, here, here. We keep picking x values closer and closer to whatever one is here. I can't pick that one because it's undefined. My graph is undefined there. But I can keep getting closer and closer and closer. You know, like a little kid, not touching you, I'm not touching you, I'm not touching you. And they're like hovering you, being annoying. So it's kind of like that. So you get closer and closer. So as your x's get closer and closer to this purple asymptote, that x value, from the right, your y value, so you have to remember, x is this value, y is this value, your y value approaches negative infinity. So they're going off in different directions. If somebody asked you, what is the limit as x approaches whatever this x value is right over here, and they didn't say from the left or the right, they just said in general, the limit does not exist. So that's something I want you to keep in your mind, okay? Now, really from the left and the right, it doesn't exist either. This is also important. It doesn't exist either, but we say infinity or negative infinity because we're describing more so why it doesn't exist. When you learn limits later on, you're going to learn that a limit is, you know, the y value that you're getting closer and closer to. Infinity is not a number. It's not a tangible place you can go. So when we say, oh, the limit is infinity, that's sort of a subset of does not exist, just a little bit more specific. Anyhow, that was your little bonus lesson. You're welcome. And then over here, that goes over there. And this part, I don't know, I really made this pretty solid over there. Repeats, repeats, repeats. Okay. So usually I've been going over these graphs in yellow once I know what the actual shape is. Ooh, smudgy, smudgy, smudgy. It's okay. There we go. So I have all that drawn. Next up, I usually take care of my h value, and the h value is our horizontal, you know, phase shift, and we have a plus pi over 5. If I want to label my first tick mark, I'm going to go right over here, and I'm going to label this with negative pi over 5, and we have been leaving a little bit of space next to it in the event that we need a common denominator, which happens quite often. There we go. So this over here is negative pi over 5, and this is also when we wait to draw in our y-axis. I don't know, are these all going to be negatives? Will I have only 1 negative and 4 positives? Will 4 be negative, 1 we'll see, right? Now, 4 more. How do I figure out how much I add? Well, you should know, right, that the distance from first to last tick mark of one cycle is p, or the period, and our formula for the period is for sine, for cosine, for cosecant, and also for secant. The period formula is, because it's normally 2 pi, and then we divide it by b because that value is going to be our horizontal stretch or compression, and it works sort of in that opposite way than we expected. If it's a 3, it compresses it. If it's a 1/3, it stretches it. So by dividing, takes care of that. So our b value is 4. So that means the period is 2 pi over 4, which I can reduce to pi over 2. But I don't want to add that last one and only get that. And then what? Find midpoints? That's annoying. Again, fractions. We don't want to deal with that. So we're going to find a quarter. A quarter of that will be 1/4 of it. A quarter is 25 out of 100, or 1 over 4 reduced. Of means multiply pi over 2. 1 times pi is just pi, and 4 times 2 is obviously 8. Pi over 8. So I'm going to add pi over 8, pi over 8, pi over 8, pi over 8 4 times, and I'll label my x-axis. However, they don't have a common denominator yet, so I'm going to find that common denominator. So, see, today I was a little better. I did my work not inside the graph. All right, so my h value was negative pi over 5, and my q is pi over 8. My common denominator will be 40. That's the least common denominator. It's not always the product of your denominators, so if you need help with common denominators, still flip back to another video because I've gone over it many times. So I'm multiplying this on top and bottom by 8, this on top and bottom by 5. This new h value we could look at is negative 8 pi over 40, and my q, don't mix them up, is 5 pi over 40. So that means this is negative 8 pi over 40. Hey, no, there's nothing there. There's nothing there. He wants, I don't know what he wants. Plus 5 pi over 40, so negative 8 plus 5 is, no, negative 3 pi over 40. Oh my gosh. Hey, no, come here. Come here. Come here. What's this? Come here. I have nothing. Plus 5 is 2 pi over 40 for that next one. Over here I have plus 5 more is 7 pi over 40. And 5 more on top of 7 is 12 pi. Make sure you see that that's a 12. 12 pi over 40. We got all of our x values labeled. Here I have a negative, here I have a positive. That's my x-axis. So my y-axis has to happen somewhere in between those, a little bit closer to this, but whatever. We're just gonna do our best. Go in here and draw my y-axis. And then here, I got a tick mark for my 3 numbers that we care about right now. That's 8. This one is 8 and 2/3. And this one over here is 7 and 1/3, right over there. A little squashed, but we did our best. We did great, much better than I usually do. Obviously, this is just one cycle. It repeats itself forever and ever and ever. I guess I could label a little bit more pink action over there. And there you go. We have an entire graph of cosecant. So I'm just going to point out a couple things here. There's the b value that helped us get our q. And there it is, the 4. And then q is how much we do to add. Oh my gosh, he's still going. To get all of those points over there. Domain and range. I'm actually going to do that in a video right after this separately because I am going to do it with you as a class, you know, kind of all together at the end. But if you wanted to watch that video ahead of time, depending on which class you're in, like different classes I do different things, but I will have it in a separate video because I don't want to like overwhelm this one. So if you feel pretty good about this and you're like, you know, I'm getting sine and cosine and it doesn't seem so bad to really just take your sine wave, pretend the whole time it's sine, take your sine wave, everywhere you have a 0, reciprocal, it's what now? It is, oh, I never put a title on this video, that's sad. It is from there, I had the title already, it was just hidden. Well, there it is at the end. You're gonna have undefined or vertical asymptotes there, and hey buddy, I think he got a treat stuck under the bag over there. I'm distracted now. So if you feel pretty good about doing that, sticking in those asymptotes and kind of thinking of it as like this little hump and this little hump flips over, and it makes a new graph, reciprocal, reciprocal, I don't know, whatever you have to do to help yourself remember, then you're in pretty good shape. Give it a thumbs up if you got the homework example right all by yourself, or even if you think you got it like 80% right, 70% right or better. If you think you would give yourself a 75% or better, give the video a thumbs up for yourself. And then if you think like, no, actually, I did not get a 70% or better, put a thumbs down on the video. All right, that just means we need more practice. And if we don't need more practice, then we keep moving. If we do need more practice, then we take a day and we practice graphing. It's fine. So I was also going in. The horizontal dotted line right here is our sinusoidal axis. This is the equation of it. Horizontal lines have equations of y equals a number. Hey, stop. Vertical asymptotes have equations of x equals something. So I could say like x equals negative 8 pi over 40, x equals 2 pi over 40, x equals, or we could say x does not equal, like, because really it's undefined. But yeah, so thumbs up, thumbs down. I hope you feel pretty good about it. And for the domain and range, that'll be for you to click through and look at the end of this video, I hope. Hopefully soon. All right, have a good night.